Just a reminder, right now we are talking about composite structure. Just to keep in your mind, composite structure is suitable for high-rise building. High-rise building. I'm talking about building probably more than 50 floors. 60, 70, 100, something looks like this. Probably your column can be composite columns. We have two cases for composite columns. The first one, we have steel column embedded in concrete column. And we have reinforcement. Looks like this. This called encased composite column. The other shape is filled composite column. We have steel tube. This steel tube filled with concrete. Sometimes this steel tube looks like square or rectangle tube, which called HSS. If you open the steel tables, you can find section properties for HSS. Last meeting, I told you we have something called composite column. Composite beams. Guys, please pay attention to me. Pay attention. This is for your information. For your information. If you have a steel beam and we have concrete slab, like this, and the steel beam looks like this, if you don't have, please pay attention, if you don't have connection between the top flange of the steel beam and the concrete slab, this beam is still steel beam. You need to figure out what is the M ultimate and make sure M ultimate is smaller than or equal phi Mn. Phi Mn, we have cases for steel beam only. So when this slab and this steel beam will be composite only if this steel beam and this concrete slab connected together with shear connector. We have different shapes of shear connector. Probably in the steel bridge or composite bridge, here is the top flange of the steel beam. Sometimes this shear connector looks like angles welded to the flange. This angle is repeated like this, angle or channel sometimes. But the most common connection excuse me, The most common connection between the concrete slab and the steel beam is this type of shear connector that we covered last meeting. Looks like this one. This is the common shear connector used to connect the steel beam and the concrete slab. If you have this connection, I can say this beam is composite beam. So please make sure what is the situation. Do you have concrete slab? Yes, we have concrete slab here and we have concrete slab here. Do you have a steel beam? Yes, we have a steel beam here and we have a steel beam here. Do you have shear connector? No, you have a steel beam. Your design should be looks like steel beam. If you have shear connector, yes, this one will be called composite beam. The slab and the steel beam working together. That makes sense? That makes sense? Guys, Brock, Brian, Roberto, can you hear me? Because Oliver saying he cannot. Okay, looks good. So please, doesn't mean, it doesn't mean if you have steel, concrete slab and steel beam, you have composite. No, we have a third key, a third part, which is the shear connectors. Shear connectors. Connecting provide mechanical connection between the steel beam and the concrete slab. Without this shear connector, we don't have composite. We don't have composite bonding. This bonding between concrete slab and steel beam is not a big deal. It will be broken at a very little load. Okay, so if you have example like this, and we need to design, because one of you will say, hey, Dr. Ayman, previously, when we started to design a steel beam, you gave us steel beam supporting concrete slab. And you told us each steel beam is supporting from center line to center line. And we designed this beam as a steel beam. You didn't say it's a composite. However, we have a steel, we have concrete slab. Yes, we have concrete slab, we have a steel beam, but we don't have shear connector. So this one still steel beam. And the concrete slab does not work compositely with the steel beam. But if you have example like this, and your cross section or your steel beam is connected to this concrete slab with this shear connector, we have composite beam design. That makes sense? Because this one or this point is a confused point. Make sure you understand this one. So right now we have example series of 45 feet span. This is one advantage of composite beam. Steel beam, your span probably 15 feet, 20 feet, 30 feet. That's good. Probably 40, okay. But if we have a span 40, 50, 60, probably 100 feet. We suggest this span or this beam will not be a steel beam. We suggest to make it composite beam. That makes sense? So steel beam, composite beam, أيوة, and concrete beam or reinforced concrete beam that we covered last semester. This span between 5 feet, 10 feet, maximum 20 feet. If you would like to increase the span 30, 40, 50, 60, 100, we need to change the structure system or the structure element. We have 3 different selections: concrete beam, steel beam, composite beam. If you have longer span, go ahead and use composite. You have to make the concrete slab compositely connected to the steel beam. If you have longer and longer, 200 feet, 300 feet, no, we need to change this statical system. I will not use beam. I will use different frame, truss, arch, something like this. It's not our point right now, but we have a series of 45 feet span composite beam at 10 feet center line to center line. So the beam is supported by 2 supports and has a span equal 45 feet. And the spacing between this beam and the following beam, we have another beam here. We have another beam here. And the spacing between the 2 beams, center line to center line, is 10 feet. Carrying the load shown below. We have dead load, we have live load. The beam are ASTM A992 based on this type of steel, F yield equal 15. The concrete has F prime C equal 4 KSI. So this one for compressive strength of concrete. Design a typical floor beam with 3-inch 18-gauge composite deck. So we have corrugated steel sheet here with depth 3-inch, and we have 4.5-inch concrete above the top of the deck. We need to select an appropriate beam and determine the required number of shear studs. What do you think about this steel beam? W what? Time what? And this shear connector, how many? First of all, we need to do loading. What is given? Slab. The square feet of this slab weight 0.075 kb per square feet. And the beam weight is assumed 0.008 kb per square feet. Assumed. Superimposed dead load, finishing, covering, sealing, all of this stuff, 0.01 kb per square feet. So if these loads are given, so I need to use these values. All of these values are given as kb per each square feet of the slab. Okay, If you would like to get the dead load on this beam as distributed load, okay, I will multiply 0.075 times 10 plus 0.008 times 10 plus 0.01 times 10. I'm sorry, why times 10? Because each beam is supporting from center line to center line. So this span or this distance will be 10 feet. So I will convert from surface load to distributed load. So the value of the dead load will be 0.93 kb per foot. The value of the live load is given 0.1 kb per square feet. Okay, 0.1 times 10 feet equal 1 kb per foot. So if you would like to get W ultimate, which is 1.2 dead load plus 1.6 live load, 1.2 times 0.93 plus 1.6 times 1, your value will be 2.7 kb per foot. So we have a span of a beam with a span length 45 feet and uniform distributed load, how much? 2.7 kb per foot. Can you tell me what is the value of M ultimate? Yes, I can. If you have simply supported beam with uniform distributed load, your moment will be WL squared divided 8. 2.7 times 45 squared divide 8. 687.5 kb foot. So the ultimate or the factored moment on this beam will be 687.5 kb foot. Any question so far? Guys, just to make sure you can understand this point. I'm so sorry. The problem said the beam weight is given as area load. It's assumed 0.008 kb per square feet of the slab. This is the reason why I multiplied the weight of the beam by 10. But if the weight of the beam is given like 80 pounds per foot, okay, I don't need to multiply it by any because it's uniform load, uniform distributed load, line load per each foot. But unfortunately, the weight of the beam is assumed as a value related to the square feet of the slab. So I multiplied it by distance center line to center line. Any questions so far? Just for your information, this technique of loading is very important. You have to understand this technique of loading. It's a very, very, very important for your FE exam and PE, especially PE exam. Okay? Okay, this is the applied moment. We need to get the design strengths of this composite beam to make sure that the M ultimate is smaller than or equal the design strengths. But the steel beam is not given, so we need to assume steel beam and design and calculate the design strengths and check. So what do you think? Which cross section I'm gonna assume? Any suggestion? Where is the table of steel sections? Yes, this one. Okay, we have different cross sections. So which one? Let me give you something here. 45. Any suggestion? Okay, let's go down and we can assume 30. Okay, I will start with 30. Okay, I will select this one. Assume your cross section is W30 times 148. 30 times 148. So I assumed W30 times 148 area gross, how much? What is the depth? From the cross section, the area is 43.6 inch square. The total depth is 30.7. So guys, we have this cross section right now. This thickness, the total thickness of the slab is 7.5. And this depth of the steel beam, 30.7. And the area gross of this steel beam, 43.6. I believe the neutral axis will be within the concrete slab. I think the top part of the above the neutral axis under compression in concrete 0.85 F prime C, and this depth equal A, and we have a compression C, and we have steel here under tension. My question is, anybody can tell me what is the width of the concrete slab which is working with the steel beam? Do you remember last meeting I called it B effective? B effective has two values, and we are going to use the smaller one. The first one is span divide 4. The second one is spacing center line to center line. I think the center line to center line is given 10 feet. That's right. Which is 120 inch. Span divide 4, 45 divide 4 equal 11.25 feet, which is 135 inch. I think I will use the smallest value. So this B effective equal 120 inch. Just a reminder, the value of capital C, 0.85 F prime C, P effective time A, 0.85. F prime C is given in the problem for KSI, 4. P effective 120 time A. The value of T, which is the tension or the tensile force in the steel beam, equal area gross of the steel beam time F yield. Area gross from the table based on the assumed steel section 43.6 time F yield 50. Ferrochromium C equal T. So 0.85 time 4 time 120 time A equal 43.6 time 50. The only unknown is A. Let's see. 43.6 time 50 divide 0.85 time 4 time 120. This one equal 5.3 inch. So the nominal moment equal area gross F yield, which is T, time total depth minus A divide 2. Area gross 43.6, F yield 50. What is the total depth? The total depth. This total depth 7.5 plus 30.7. The total depth is 38.2. This one equal concrete thickness plus steel depth minus A divide 2. Now I can figure out the value of Mn. Equal 77,499 kb inch. Divide this number by 12. I will get 6,458.25 kb foot. That's fine. No problem. We don't have issue, but the value of M ultimate, the value of M ultimate 687. Wow. I forget something. Phi Mn. We need to multiply this value by 0.9 Phi, so it will be 5,812. Okay. Phi Mn equal 5,812 kb foot. Wow. I think M ultimate is smaller than Phi Mn. Your cross section will be safe, but I'm sorry, it's more safe. The applied moment is 600. The design strength is 5,000. You are kidding. You select very, very big cross section. For your exam, you will say it's safe and we need to reduce it and that's it. But for your real design, no, we need to reduce this cross section. Rather than W30, we can go down more, and because 5,000 is too much, 5 times. So probably we can go down for W20, W14. Yeah, we can try W14 for time something, or W16 time something, or W20, 18. So we need to go down.
Okay.
Does that make sense? Go ahead.
I'm really sorry, but can you go back to the very first page when you solved for M ultimate really quick?
This one?
Yeah, M ultimate. The next page.
There you go. W ultimate and M ultimate.
Oh, kip foot. Okay. Alrighty. I'm sorry. Never mind. Thank you.
Okay. Yeah. So did you get this idea? We have the applied moment is 687. However, the design strength is 5,000. It's okay, it's safe, but it's not economy. We need to reduce that selected cross section. That makes sense? So if you have time, we will try another one. Another smaller steel section. We assume W30, I will assume W20 or 18 or 16 times something, probably. Okay, assume we will accept this cross section. We need to figure out how many shear connectors. Do you remember last meeting? I told you capital N equal summation Qn divide Qn. If we go back, here you go. The number, I will not say the required number. No, I will say the number of shear connector capital N equal summation Qn divide Qn. Just a reminder, summation Qn equal area gross time F yield. Very easy. The area gross, I will accept the assumed cross section. So the area gross 43.6. F yield equal 50. 2180 tip. Qn nominal strength of one shear connector. I will figure it out from this table. I will figure it out from this table, step by step. My question is, in this problem, do you have corrugated steel sheet? Yes, we have designed a typical floor beam with 3-inch 18 gauge composite deck. So we have corrugated steel sheet. We have corrugated steel sheet. So we are in this case or this case. If you don't have deck, we will be in the first one. So there is a deck, steel deck. What else? Which one I'm gonna use? This one or this one? Do you know what is the difference? Deck parallel, deck perpendicular. I'm sorry, I cannot understand. Okay, the steel deck looks like this. Which is parallel to this direction. That makes sense? Your steel deck looks like this. This is a cross section. So if you have a steel beam here, I believe this steel beam, the cross section looks like this. Here is a concrete. This one or this case, the steel beam parallel steel beam is parallel to the steel deck. That makes sense because this steel beam is parallel in this direction and this deck is parallel in this direction also. So both of them are parallel. But if we have a steel beam like this, which is parallel in this direction, so I believe your cross section looks like this. This edge, and we have another edge, and the top edge is the top of the concrete. So your steel deck is parallel in this direction. However, the steel beam parallel in this direction. So in this case, steel beam is perpendicular to the steel deck. So what do you think about this case? Did you see any shape of the corrugated sheet which looks like this? No? So our steel beam is perpendicular to the steel deck. Perpendicular means we are in this case. So guys, as I told you one more time, because this table is existing in the AISC, how can I read it? We need to figure out what is the type of slab. Is it without deck, steel deck? Do you have steel deck? Okay. The steel beam is parallel or perpendicular? I think you have to look to the cross section. If your cross section showing up the profile of the steel deck like this, which is corrugated, okay, both of them are parallel. If not, the steel beam is perpendicular. So I think our example, steel beam is perpendicular. So we are in this case. Which one I'm gonna use? This case or this case? We need to provide more details about the corrugated steel deck, so I will assume any of them. Weak stud bare rib. Okay, I will assume the first case. Then, how many studs bare rib? How many? Stud bare rib. We will assume one stud. What is the diameter of the stud anchor diameter? Okay, we have different 3/8, 1/2, 5/8, 3/4. The most common one is, I remember, 5/8. I remember this one, 5/8. So we will assume it 5/8. Then, do you have normal weight concrete or lightweight concrete? Please read your problem carefully. Do you have any information about special type of concrete? No. So we are in the normal weight concrete. What is the value of F prime C? It's 4 KSI. So 4 KSI. So your strength will be 12. So we have steel deck perpendicular to the steel beam. I assume the weak strip or weak stud per rib. How many? 1. What is the diameter? 5/8. The F prime C is 4 KSI. So the value, the nominal strength of the shear connector is 12. So the value of Qn equal 12 kip. Go ahead and put your numbers. 2180 divide 12. I believe we will get too much. We need 181.67, doesn't make sense, so I will assume it 182 studs. Do you think this is the total number required? No. No. Because this N is the required number between the maximum moment and the zero moment point. We need here capital N equal 182 studs. That means we will need another 182 studs on the other side. So the total number of studs will be 364 studs. One of you will say 364 studs is too much. I agree with you because you didn't select the most efficient cross-section. Guys, the selected cross-section, which is W30 times 148, is not economic. It can give you the design strength 5,812. However, the required is 600 only. So you selected an economic cross-section. It's not economic. So this heavy cross-section will cause too much number of shear connectors. That makes sense? Do you know why? Because the nominator who is responsible to get the capital N number equal area gross F yield. And this area gross of the selected steel beam. Because you selected an cross-section which is not economic, this area gross will be too much. So the summation Qn is too much. So the number capital N is too much. That makes sense? So the final conclusion, if I assumed my solution is correct, the final conclusion, I will assume the selected cross-section is safe, which is W30 times 148, and the total required number of shear connectors to make this beam to be composite, 364 shear connectors.